Hello again. Today's video we're going to be talking about the derivatives of inverse trig functions and logarithms. Okay, so why haven't we talked about derivatives of inverse trig functions before now? Well, it turns out that in order to derive the derivatives of the inverse trig functions, you need to use the chain rule and implicit differentiation. So that's why we've saved this topic till now. So I'm only going to derive one of the inverse trig functions just to show you how it's done. I won't derive all of them, although I will write up all of the formulas for them, and then we'll do an example or two. Okay, so first, let's consider the function y equals inverse tangent of x. And I want to come up with a derivative rule. I want to solve for dy dx, okay? Well, I don't know a derivative rule for inverse tangent, but I do know a derivative rule for tangent. So what we can do is we can just use the fact that if y is the inverse tangent of x, that means that tangent of y must equal x. That's the definition of inverse tangent, how it works out. Basically, if you take the tangent of both sides, the tangent and inverse tangent cancel on the right side because they're inverse functions. Anyway, now that we have tangent of y equals x, and I want to solve for dy dx, I'm going to implicitly differentiate. I'm going to take the derivative with respect to x on both sides. Now the derivative of tangent is secant squared. Whoops, that's not an x though, that's a y. So we then have to multiply by the derivative of the inside with respect to x, which is simply dy dx. That was the chain rule in action. Derivative of the right side is simply 1. Therefore, dy dx is 1 over secant squared y. However, I would rather have this written as a function of x instead of like a function of y, so we need to simplify this, okay? Now, I know what tangent of y is. Tangent of y is x, but I want to figure out what secant squared of y is, and that leads me to remember our Pythagorean identities. One of the Pythagorean identities is tangent squared plus 1 is equal to secant squared. Therefore, this secant squared in the denominator we can rewrite as 1 plus tangent squared of y. Because that was y, that has to be y. Okay, and tangent of y I know is equal to x, so this denominator I can change to be 1 over 1 plus x squared. That is dy dx. In other words, the derivative of the inverse tangent of x is 1 over 1 plus x squared. All right. Now, like I said, I'm not going to prove all the rest of them, although I will write them down real quick. So let's write down all of the derivatives of the inverse trig functions. So we'll start off with the one I just proved. The derivative of inverse tangent is 1 over 1 plus x squared. Next, the derivative of inverse sine is 1 over square root of 1 minus x squared. The derivative of inverse secant is 1 over x times the square root of x squared minus 1. Okay, so here are 3 of the inverse trig functions. But there's 3 more inverse trig functions. Let's write those down. So we've got inverse cotangent, whose derivative is negative 1 over 1 plus x squared. We've got inverse cosine, which is negative 1 over square root of 1 minus x squared. And we've got inverse cosecant, which is negative 1 over x square root of x squared minus 1. So you may have noticed something, that the derivative of inverse cotangent is exactly the same as inverse tangent, except it has a minus 1 on the top instead of a plus 1. And this one is the same as this one, but multiplied by negative 1. And the same thing for the derivative of inverse cosecant is simply the derivative of inverse secant times minus 1. So hopefully that will get you to memorize, help you memorize those 3, that you really only have to memorize inverse tangent, inverse sine, inverse secant, and then remember the relationship between those three and the other three. Okay. Also, another thing to note is, when it comes to derivatives of the regular trig functions, it was the three trig functions that started with the letter C whose derivatives are negative. And once again, the derivatives of the three inverse trig functions that start with the letter C are all negative. So maybe that'll help you memorize them as well. Okay. Now, as it turns out, the derivative of the logarithm, the natural log, you can also prove this using the fact that logarithm is the inverse function of the exponent, and prove it in a similar way for the inverse trig functions. Basically, any function that is the inverse of another function, you should be able to use implicit differentiation to come up with a formula for its derivative. But anyway, the derivative ln of x is 1 over x. I think I've written this before. And the derivative of log base b of x is 1 over x times 1 over ln b. Okay, so these derivative rules, as I explained, you can prove using implicit differentiation. However, on tests, you don't want to be proving them before you actually use them. You want to memorize these. Okay, so, and like I said, you really can just memorize these three and then remember the relationships to get the other three. Okay, now let's do a couple of examples of derivatives of inverse trig functions. All right, let's start with f of x is going to be the inverse secant of e to the x, and we want to find the derivative. Okay. The derivative for inverse secant was 1 over x square root of x squared minus 1. Notice, as I was saying that out loud, I was saying x, but I was putting a parentheses. That's because this is not just an x inside of it. So we're applying the chain rule. So every x in the formula you have to replace with e to the x. And then times the derivative of the inside. So that's our derivative. Oops, I wrote inverse function. That should be derivative. Okay, sorry about that. Then we can cancel an e to the x out of the numerator and denominator, and we can rewrite e to the x squared as e to the 2x. There, and that's our derivative. Not too bad, a little bit tricky, that our formula for the derivative inverse secant has 2 x's, so you have to plug this in twice. Anyway, let's do yet one more example. This one's going to be a little bit longer. Instead of just finding the derivative, let's find the equation of the tangent line to inverse tangent of x times y equals pi times x at 1/4, 4. All right. So an implicit equation, so I'm going to implicitly differentiate. So I'm taking the derivative with respect to x on both sides. Derivative inverse tangent is 1 over 1 plus x squared. And then you fill in here xy. And then times the derivative of xy. The derivative of xy, that's a product, so we have to apply the product rule. So derivative of the first times the second plus the first times the derivative of the second, which is dy dx. Or if you want, you can put y prime, but I prefer writing out the full dy dx rather than y prime because you might lose that prime. You might think it's like y to the 1. So dy dx helps you not confuse it for something else. Anyway, the derivative of the right side is simply pi. Okay, we're trying to find the slope or the equation of the tangent line, so we need to find the slope of the tangent line. In other words, we want to solve for dy dx, but we don't need to solve for it like at all points. We only need to solve for it at this one point. So I would advise just plugging in that point right now, then solving for dy dx. Okay, so y is 4, x is 1/4. So that's the top of the fraction. And then the bottom, x times y is 1/4 times 4. Well, that's just 1. 1 squared is 1, plus 1 is 2. So now we have this equation. We can multiply by 2 on both sides. Then we can subtract 4 from both sides. And finally, multiply by 4. So dy dx is 8 pi minus 16. So that is the slope of the tangent line at that point. Now we just need to put that into the point slope equation to get the equation of the tangent line. Okay, so let me make some room here. That's my slope, that's my point. Put both of those into the equation of the line. So y minus 4 equals m, which is 8 pi minus 16, times x minus 1/4. Okay. Distributing, although I'm going to leave that as just one thing, times the x, and then this times minus 1/4. 8x times minus 1/4 is minus 2 pi. I'm sorry, I said 8x, that was 8 pi times minus 1/4 is minus 2 pi. And then plus 4. And then add 4 to both sides. So y equals 8 pi minus 16x minus 2 pi plus 8 is the equation of the tangent line. That's the slope, that's the y-intercept. Oops, that shouldn't be an x, that should be a pi. There. So that's your slope and that's your y-intercept. Alrighty, so I think that's enough examples for today. I'll get this up on my website pretty soon, and hope that y'all are finding the videos helpful. If there is any problems you would like me to look at, leave a comment, and if I see it, I'll try to do an example of something like that. Anyway, so hope y'all are having a good day. See y'all there.